In this video, I'll be talking about gyroscopes and how they pertain to the flat Earth debate. It is expected that high-precision gyros should be able to detect the angle differences of a curved Earth due to their rigidity in space. This is true, yet airplane artificial horizons, employing some of the best gyros available, do not show this curve. Other people have tested for curve using their phone's sensors, bubble levels, or other electronic MEMS devices over a long flight or drive, and found no angle differences, such as in this video put out by Seventh Day Truth Seeker called 213.47 Mile Lake Erie Globe Curvature Test, Flat Earth, and mirrored by Globebusters under a similar name. I'll be referencing that video later due to its excellence in one respect. Prior to this test, Seventh Day Truth Seeker proved that his phone was capable of reading a slow angle change over a couple of hours to within 6/100ths of a degree. So, in his 213-mile test, the device could surely detect the expected 3-degree change over a few hours, right? It looks to me like his pretest uses this app, which I loaded onto this device here. It can measure angles really well, just as he observes. But there's something crazy important about this video you're looking at. It's important. What is it? This is a Kindle Fire 5th generation, as seen in the settings. But so what? Here it is. According to the specs, none of these basic Fire tablets, including the 5th gen, has a gyro at all. And here it is confirmed in Android sensor box. No gyro. Whoa. How is it telling me the angle if it doesn't have a gyro? Well, it doesn't have a gyro, but it does have something else, an accelerometer. I'm now going to say something possibly outrageous. If you rage quit the video after this statement without sticking around for the proof which will follow, then you're not really interested in the truth. I'm going to tell you right now that angle comes from the accelerometer, not the gyro. That answer is obvious if this device does not have a gyro, but it's still the key answer even for devices which do have gyros. Unfortunately, the flat earth thinking related to airplane horizons and travel tests is all flawed with this same confusion. They think they're testing gyros, but they are not. What? You're crazy, I hear someone say. Airplane horizons are gyros, you liar. My answer, you're only mostly right. According to specs and trainings, they are gyros, but with accelerometers built in. In the long term, the accelerometer is the master. It levels the gyro fast enough to keep it level in spite of curvature. The accelerometer is the master. That information is in the specs, but hey, experiments are better. And Wolfie 6020 actually obtained a gyro and showed us experimentally that the gyro seeks bubble level. It's not happy to stay in whatever orientation you started in. It bubble levels. This is not the behavior of a pure gyro. But what about the MEMS device in Seventh Day Truth Seeker's test? Globebusters Bob has declared emphatically that it gives clean gyro output based purely on inertial changes and no reference to gravity, except for perhaps at the beginning in a calibration. But let's look into that. Seventh Day Truth Seeker's vid is full of technical details, which is Truly excellent. This is the good thing about his video. He deserves serious kudos for that. I want to draw attention to this slide. In the note, it says that angle of z-axis will have accumulated error because there is no magnetic field correction. The gyro is not up to the task for that angle. The truth is that no existing MEMS gyro is good enough to do stable angle readings over the long term. But the other angles have high accuracy and stability. Why? The answer is, once again, super, super important. Here's the start of the answer. Over here it says the angles are calculated, which is what we would expect from a non-physical MEMS gyro. Those gyros do not maintain rigidity in space. Instead, they feel the forces of the turn, and using math, they can then translate that into angles. But it is done by calculation. The slide adds the detail that it uses a Kalman filter. The significance of that will emerge. But even before you go to the trouble of looking up what a Kalman filter is, this slide is trying to scream the answer at you.
Kalman fusion filter combines the gyro and accelerometer to get high precision angle measurement.
What did he just say? He said it fuses information from the gyro and the accelerometer. What does the accelerometer have to do with the angle? Well, by now you know the answer. I went on Amazon looking for the part Seventh Day Truth Seeker used. I believe this is the product he bought. No, the seller is a Leckmaster, and the part number is BJY61. And to the best of my ability to discover, this is the product manual, uploaded by a Leckmaster a few years ago. Again, the manual tells us that the purely calculated Z angle is only valid short term. Now we go down one more line. And oh snap, there's the answer. The X and Y angles are filtered by gravity. The accelerometer feels gravity. But wait, a flat earther says gravity doesn't exist. Prove it first. Well, I don't care if you call it gravity or buoyancy or John Jacob Jingleheimer Schmidt. It's that thing that pulls things downwards. And accelerometers feel it. And the tablet can bubble level and measure angles from it. Here, I'll show you. This is Android sensor box showing a graph of my raw accelerometer data. Each of those lines, red, green, and blue, corresponds to one of the accelerometers aligned with X, Y, or Z. That red line says, yeah, I feel you shaking me left and right. That blue line says, yeah, I feel you shaking me top to bottom. And that green line says, yeah, I feel you shaking me front to back. But see, that green line is steady state above the red and blue lines. Why is it up there? Well, it's saying, I feel something steady pulling at my back. If I tilt vertical, the green sensor doesn't feel it anymore and drops back down to 0. But the blue line is now high, saying, hey, I feel a pull at the bottom. The same will happen if I tilt on the side. If I go somewhere between, both or all three will feel some of the pull, but not as strong because it's off axis. When the chip considers what all three axes feel, it can accurately point a digital finger straight at the ground relative to itself and tell you the angles. No gyro needed, as we already know. This thing doesn't have a gyro. But wait, another person says, I know now somebody's trying to pull my leg because that doesn't make any sense. People build sensors with gyros that aren't good enough, and according to you, a gyro is not even needed. As though a manufacturer would even do that. It must be baloney. My answer? No, gyros are still useful. One, recall that accelerometers in gravity can only stabilize x and y angles. Z angles, it can't help. And unless there's a compass input, the gyro is the only source for z. But beyond that, accelerometers can be confused when there are other forces besides gravity, as demonstrated here as I shake around the device. And they don't have a clue what's going on while in free fall. As you can see, all the readings were close to zero during free fall. So at any given moment, the accelerometer may be speaking nonsense. So the gyro is used for all short-term readings and is trusted emphatically in the short term. It just can't be trusted long-term due to tiny drifts that happen little by little and build up to something bad in the long term. The thing about the accelerometer is that while it can't be trusted in the moment, it can be trusted on average over time. In order to get the average grossly different from gravity for several minutes, you either have to be on a zero-G parabolic flight, or else something mad is happening, and you'll probably soon be dead. But even in such situations, sufficiently smart software can decide what's going on by combining gyro and accelerometer data. Mentioning smart software brings us back to the Kalman fusion filter. I guess we'd better look it up now, though it's a bit hairy. I studied this and a navigation-related example for quite a while, and will sacrifice much for brevity while I try to share my already imperfect understanding. Kalman filtering is a software concept, not specifically related to navigation, but can apply to a lot of things. The way you visualize Kalman filtering is with clouds, where the right answer is believed to be somewhere in the cloud, but you're not perfectly sure where. So Kalman filtering is for uncertain data. If you have absolutely reliable data, you don't Kalman filter. You use one type of data to predict how the cloud will change in the near future. Then try to measure the cloud directly with another type of data. Your predictions and measurements are compared and combined into a new cloud, hopefully smaller and more certain, used for the answer reported to the user and the start of the next iteration of the Kalman filter. To use our angle example, suppose we are reporting down as 0 degrees right now. The gyro says, well, if that's down now, then based on the 5 degrees per second x rotation I feel, next time we measure in 1 second, I predict down to be 5 degrees x. The accelerometer can then report, well, here's what I've recently felt. Down is probably somewhere in this cloud. If things are favorable, it can report a tight cloud with high certainty, which when combined with the predicted answer nudges things in the right direction. If we are in free fall or things have been too crazy, the accelerometer can report a huge cloud, which in essence says, from my viewpoint, down could be anything, I don't know. When that's combined with the prediction stays pure unchanged, in essence putting the gyro in control until higher certainty can be measured. Here's an example of Kalman filtering used for navigation. It's similar to our case because it's also about motion. Read it if you want a deeper understanding. In the case of this example, they're figuring position, not angle, but if you study it, you will better understand the concept of Kalman filtering. That's enough heavy theory for now, but here are the main takeaways. 1. This device says it uses a Kalman filter. 2. Kalman filtering insists that two types of data are input into it. 3. The video reveals that the two types of inputs are gyro and accelerometer. 4. Kalman filtering performs continuous integration of these two data types. It is not a case of initialize via gravity, then go pure gyro. That would be contrary to the definition of a Kalman filter. 5. If you consider the preceding facts, and even more so if you will get into the nitty-gritty of Kalman filtering and understand the prediction, measure, and combine steps, then you can see that logic strongly indicates that the device is bubble leveled, just like the airplane gyros. So we get a device which is very good at what it's designed for. For example, having your phone knowing what you're doing with it and being able to respond to that somehow. Or, incidentally, it can accurately measure angles off of gravity all day. But you don't get a device capable of measuring the angular change of the Earth over 200 miles in 2 hours. A job, in fact, completely incompatible with its design, since it constantly uses gravity to give you angles which, unlike Z, don't drift over time. It says so in the manual. And it's consistent with the logic which starts to whisper as soon as you start to ask the question, why does the Z angle drift, but not X or Y? And it's consistent with the Kalman filter which it claims to have. In a number of ways, you can conclude that either what I'm telling you is true, or else the chip spec is fraudulent. And if so, where does that leave you? In no position to trust its output in an experiment anyway. This 213-mile curvature test, sadly, is not an experiment. It goes through the motions of being an experiment. It took time, money, effort. Other flat earthers have gone through this motion as well, on planes and in cars, using their gyros, or so they think, and say that they're doing real work while we sit here on our behinds and do nothing but snipe at them. But no matter how many times they do something like this, put their phones on airplanes, or even read something as fine as its artificial horizon, it's still completely empty and pointless. They are using the wrong tools for the job so far. And if they claim to buy the right tool for the job, even for many thousands of dollars, and try again, boy, am I going to make sure by reading the spec myself. Because sadly, the only thing these experiments have proven so far is that those who do them and believe in the conclusions given from them don't know what the heck they're doing or talking about. But boy, are they willing to act just the opposite.